Okay, class. We now are ready to talk about skeletal muscle resting membrane potential and its action potential. Previously, we had talked about the neuron, and prior to that, the resting membrane potential of all living cells. Okay. Before I do that, I want to bring something up, though. Okay. Do you remember when we first started the electrophys, I showed you this. I said how to study it for me. Print out this document here that I just wrote, and you can see I'm still editing. You'll have a nice copy of this. Look at the electrophysiology videos that I'm making in association with this, and read in the text and so forth, motion pictures. But I also mentioned that I had some PowerPoints already known as general electrophysiology and electrophysiology of muscle. Those are the ones that your tutors would know about, which were the ones I normally would use in class because I was teaching face-to-face. They're a little more advanced. So realizing I wasn't teaching face-to-face, that's why I took time to write this document and, of course, make these videos too, since I'm not face-to-face. But now that you've gone through most of this document, we're almost getting to the end of it, a few more pages, you now can go, if you'd like, and look at general electrophys and electrophysiology and muscle. Because in those documents, I also do things like this. I show the events of a neuron action potential. See, like event 1, 2, point to everything, 3, 4. So you have a lot of material that I've done, and this is the most recent I've done to try to make it a little easier for you since I'm not doing face-to-face. And of course, once I've done it, then even when I go back to face-to-face, you'll be available for people to study. All right. Now, we're getting to skeletal muscle resting membrane potentials, action potential. We have 3 types of muscle in the human body. Cardiac muscle, which is in your heart. Skeletal muscle, which is hooked to the skeleton. That's what you move your arm with and your leg. And then smooth muscle in your organs, like the intestine, the bladder, or so forth like that. I'm interested in skeletal muscle, right here. Skeletal muscle. Okay, so that's what we're interested in. So we come here. These are 3 action potentials. This is the one for skeletal muscle right here, a motor neuron. Okay, but it's a nerve cell. Now look at this. This is a motor neuron, but it's still a neuron. Okay, what are the 3? What are the 2 things that can do conductivity, action potentials of nerve and muscle? This is a neuron, motor neuron. Motor neuron means it's a neuron going to a muscle cell. It's a neuron going to a muscle cell. In this case, it's really going to a skeletal muscle cell. This here is a skeletal muscle action potential. So this is a neuron, and that's a muscle action potential. This is a nerve action potential, which we just talked about, and this is a muscle action potential. All right. So let's go further now. I'll pull that up over here. All right. The muscle cell has a resting membrane potential of around a -90, compared to the neuron resting membrane potential of around a -70. The muscle cell action potential involve voltage-dependent sodium potassium gates, just like the neuron. And I'm going to put not involved, but involves. I like that better. Involves voltage-dependent gates, just like the neuron. The skeletal muscle cell sodium voltage-dependent gate does not have an activation-inactivation gate. So in other words, remember with it, there was an activation gate and inactivation in the neuron. You don't have that. It's just one. The gate opens when threshold voltage is reached and eventually closes. The potassium gate is close to the same mechanism as in a neuron. Remember, it just opened and closed. The skeletal muscle cell action potential is a little longer, and I should say in duration, than that of the neuron. See, we can see that here. Look at it. 2 milliseconds, about 5 milliseconds, let's say right there. Now this is a motor neuron, so it's a little longer. Remember I told you it's generally about 1 millisecond for a neuron, but a motor neuron is a little longer. So different neurons kind of have a different deal. But you can see this is 5 and that's 2, so it's a lot bigger. The action potentials travel around the skeletal muscle cell membrane just like they do in neurons, except the action potentials travel a little slower. Why? Because the action potentials are longer in duration. Okay. All right. Ignore this one. This is an ANP2 one. That's heart. That's AP2. Okay. We go further. Now, so that's all I'm going to say on the skeletal muscle action potential. It works exactly the same. Let me just paraphrase. You reach threshold. Threshold then takes you up because sodium comes in. Sodium gates open. Sodium gates close. Potassium gates open. Potassium shoots out, comes down, hyperpolarizes. So everything's the same. And the only difference is, when you read it, are these things I mentioned up here. All right. Now, what turns on the muscle? A nerve. So now we're looking at a neuron hooked to a muscle. See, a skeletal muscle does not automatically do its thing. It must be turned on by a nerve. And what you have, the way that works, I'm going to go here, but I'm going to show you what I'm finna say. How that works is, you have this thing called a neuromuscular junction. So a neuron comes in, this is your spinal cord, and let's say hooks to a muscle cell. Each one of these would be a muscle cell. And this is how it would hook. So it comes in, so this right here would be a neuromuscular junction. So the neuron turns on the muscle. Okay? So we go here. This would be a neuromuscular junction, let's say. Okay? But in this case, we're looking at a presynaptic and a postsynaptic. So here would be more of what we would call a neuromuscular junction. Right here, this drawing. All right, but I use this drawing because I want to talk about ligand-gated channels. So our subject now becomes ligand-gated channels. Ligand-gated channels. That's where our subject goes. So we finished talking about the skeletal muscle action potential. It's very similar to the other. Now we're talking about ligand-gated channels. And ligand-gated channels would be what's involved in a lot of things. One of which would be the neuromuscular junction. So what I'm going to do is I'm going to end this video and then we're going to start one on ligand-gated channels.